Okay, this is 2.3 linear, exponential, or neither. And it's a practice understanding task. So in this activity, they're going to give you a model. And you're going to have to determine whether the model is linear, exponential, or neither. And then they're going to ask you for two reasons for your answer. Justification. That's mathematics, you guys. So typically now, when they give you a model, one of your reasons will typically be very easy to see, but the other one, you may need another model or a rule to come up with a second reason. And that's the challenge. That's stretching us. So let's take a look at our first model. All right. This is nothing more than a graph, and I want to know, is this graph the graph of a function that is linear, exponential, or neither? So the function is, well, my first thought is, isn't this a straight line? And isn't the graph of a straight line the graph of a linear function? So I'm going to say the function is linear because, and in layman's term, I'm just going to say the graph is a straight line. Now, my second reason, all right, this is where we're going to develop a lot more understanding here. This is some introduction to some really important concepts right here. All right. Now, what I like to do, my favorite model is an explicit formula. So if I could come up with an explicit formula for the graph of this line, and that was a linear formula, that would be my second reason. So another model or rule. Well, notice that they gave you an x-intercept, and this is hard to read, so I'll rewrite that, but that's a -3/2 comma 0. So let's make that a little bigger right here. -3/2, 0. And then they give you a y-intercept down here of when x equals 0, y is going to be -0.5, or -1/2. Okay, now if I have a graph and I have 2 points that I know the coordinates of on the graph, I can find my slope with a simple slope triangle. So the explicit equation is, well, I see a slope and I see a y-intercept, so let's go there. What is my slope? Now remember the concept of slope. Slope is rise over run. Excuse me. So when I have the graph of what I think is a linear function, I choose 2 points, and then I draw what's called a slope triangle, with those 2 points being vertices of the triangle. So there's my slope triangle right there. And a slope triangle shows me my rise and my run. All right, so now think about this. I'm at y equals 0, and I'm dropping down to y equals -1/2. So that's a rise of -1/2. And then how far am I running? From -3/2 to 0, so I'm running a +3/2. So one more time, the rise is -1/2. The run is +3/2. All right, and again, go back to middle school. We're dividing by a fraction, so let's change that to multiplication by the reciprocal of that fraction. So I'm going to say that becomes -1/2 times the reciprocal of 3/2, which is 2/3. And what does that equal? Well, a negative times a positive is negative. And you see the factors of 2 will just cancel out right there. And what do I have left? 1/3. So -1/2 times 2/3 is -1/3. And that's the slope of that line. Now, sometimes they're not going to give you the graph, just 2 points. So let's practice finding the slope that way. So your rule for finding the slope given 2 points is nothing more. It's the same thing as rise over run, by the way. But rise we're going to write analytically as y⁻² minus y⁻1, which is the y-coordinate of the second point minus the y-coordinate of the first point, over, and then the run is x⁻² minus x⁻1, or the x-coordinate of the second point minus the x-coordinate of the first point. So let's do the arithmetic here. We should get -1/3 again. So m equals y⁻² would be -1/2 minus y⁻1 would be a 0 over x⁻², that would be a 0, minus x⁻1 would be -3/2, And now our arithmetic. Negative 1/2 minus 0 is negative 1/2. And 0 minus negative 3/2 becomes 0 plus 3/2, or 3/2. And we're at the same place we were over here with our slope triangle. Negative 1/2 divided by 3/2, we already worked it out. That's negative 1/3. So this is negative 1/3. So now I have a slope. So I'm going to go f of x equals, and my general formula of a linear equation in slope-intercept form is mx plus b. So f of x equals, all right, well, my slope m is this negative 1/3, negative 1/3 x, and now I only need the y-intercept, which was given to me. See that negative 1/2 right there? That's the y-coordinate of that point. That's my y-intercept, and we call that a b. So b equals negative 1/2. And there it is right there. So there's my two reasons. I've highlighted them. And now let's take this a little further. I've been introducing, is the function continuous or discrete? So look at the graph. It's a solid line. It is not it's not dashed. Therefore, it's implied that this would be a continuous function. And then the second new thing that I've been introducing is, what's the domain of this continuous function? So the domain, D, is x is in, and notice how I use parenthesis, parenthesis for my interval notation. Now, they don't put arrows typically on both ends of a line, but those are implied. So this implies that this graph is going to go on forever to the left, which means I'm approaching negative infinity. And because I can never reach negative infinity, I use a parenthesis right there. And then there's an arrow implied on the right, which means this goes on forever in a positive direction or approaches positive infinity. But because we can never reach infinity, we put a parenthesis right there. Now, if there were endpoints and a number, I would not use a parenthesis, I'd use a bracket there. But this means negative infinity is less than x, and x is less than infinity. And there you have it, the first problem. There's a lot of math on this first problem. This is good stuff. Take great notes. Make sure if you have questions, you get a hold of me. But that's exciting stuff right there. Okay, number 2, same question, but the model they have given us is this table. It's a tennis tournament with the inputs being the round number, and the output would be the number of players left. So after round 1, there will be 64 players left in the tournament. After round 2, 32. After round 3, 16, and so on. All right, so we need to decide whether or not this is linear, exponential, or neither. So the function is, well, let's focus on where do we see our pattern of change. Well, 64 goes to 32, which goes to 16, which goes to 8, which goes to 4. So it looks like we're multiplying, and what are we multiplying by? Well, 1/2 of 64 is 32. 1/2 of 32 is 16, and so on. So the common ratio is 1/2. All right, which means whenever we have a common ratio, right, if this were our sequence, it would be geometric, which makes the function exponential. All right, now I'm excited about explicit functions, so I'm going to add a 1b here. I really want to focus on the explicit functions as much as possible, and that wasn't one of my original models that I used to answer this question for my second reason, but I added that in. So if I know I'm exponential, I know my general form is f of x equals a times b, and then I need to decide to the x or to the x minus 1 power. Now look at the first term right here. And excuse me, let me let my dog out and I'll be right back. Go ahead. Sorry for the distractions. Welcome to remote learning and me creating videos at home. Anyway, where was I? Oh yeah, b to the x or b to the x minus 1. All right, well, my first input is a 1, which means I'm going to use a b to the x minus 1. If my first input were a 0, that would simply be b to the x, or guess what? b to the x minus 0, which is just x. That's how that works. All right. Now, if we know what a is and what b is, we have our explicit formula. And a in an exponential is always your initial output, 64. B, the base of an exponential, is always your common ratio, 1/2. So that becomes 64 times 1/2 to the x minus 1. So that could be our second reason right there, and we're done. But I would like to add a graph. You know me, I like models, all right? I want to see it all. So I'm just going to do a first quadrant coordinate plane up here, and we're going to call the inputs, how about we go with an input of n, and the outputs then we will call f of n. And let's go ahead and scale our hash marks on our horizontal axis by 1/2. So I'm going to put a 1 here and then continue that pattern. Very nice. And now I have to get up to 64, or at least close to it, so I probably went like something by 3, 6. So let's see. Yeah, I'm going by 6s, so 6, 12, 18, 24, and so on, and I went up to 60. Now, so when I plot this first point, when n equals 1, f of 1 is 64, well, that's going to be a little above my grid here, but that's okay. We'll just approximate it. That point would be about right here. And I'm going to plot these points with one push of the button, but then let's make sure we agree with them all. Okay, so the first point, n is 1, and f of n is 64. F of 1 is 64, so there's 1 and 64, approximately. And then n is 2, f of 2 is 32, so there's my 2, and that would be 24, and that would be, what, 30, so 32, yeah, that looks good right there. And then what is f of 3? It's 16, so 12, that looks like a good 16 right there. F of 4 is 8, I like that right there. And f of 5 is 4 right there. So look at the scatter plot right here. Picture the curve. That is not a straight line. That's exponential, and that's exponential decay. This curve, if I drew my dashed line through the scatter plot, it would just get closer and closer to my horizontal axis, but never reach it. Exponential decay. So there's a third model right there. Now, I also want to add a little bit more. Is this problem situation discrete or continuous? Do you agree that the round numbers would be whole numbers, 1, 2, 3, 4, and 5? I won't have a round 1.75 or anything like that. And also the number of players left in the tournament will always be whole numbers, 64, 32, 16, 8, and 4. So that tells me that this is a discrete function. And discrete, the domain is simply nothing more than my set of inputs. And the birdie brackets we use for set notation, okay? And my first input is a 1, and then a 2, then a 3, then a 4, then a 5. And that's as far as I see right here. But let's think about this. Is this just going to go on forever? This is a tournament, right? So I can't have infinite rounds. So let's see. At round 6, wouldn't I have 2 people left? Which means at round 7, those people would play, all right? And I have my one champion. So I'm going to say there's going to be 7 rounds. So I'm going to say X is in the set, 1, 2, 3, 4, 5, 6, 7. That's pretty cool stuff. Okay, so number 3, all they did was give us this equation, y equals 4 times x. So what kind of equation is that? What would that graph look like? Think about those things. So the function is blank because, well, what's the general form of y equals 4 times x? Isn't that the explicit function is of the form, and isn't that nothing more than y is f of x equals m times x plus b? Here it is, f of x equals mx plus b. where m is my slope, and that would be a slope of 4, and b is my y-intercept, so that's a plus 0, so the y-intercept is 0. So that is a line that goes through the y-axis at 0 with a slope of 4. That's linear. All right. Now we could create another model to give us our second reason why this has to be linear. So how about we go from an explicit formula to a simple table? So do your t-chart right there and make your x's 0, 1, 2, 3, and 4. And then what would your corresponding y's or f of x be if you want to call them f of x's? Well, 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. And I hope you see the pattern already. 0, 4, 8. Wouldn't that be a 12 and a 16? Let's double check. When x is 4, 4 times 4 is 16. Okay. So now if you look at these y values right here, what's your pattern of change? Aren't you adding a 4 every time? So the common difference is 4. And there's our second reason right there. That must be linear because we have a function that has a common difference of 4 or a slope of 4. So what is this then? Let's add the discrete versus continuous. So you have to look at the original model. All they did was give us an equation. So if I graphed that equation, y equals 4 times x, I would just graph the line like I just mentioned. I'd graph a line with a y-intercept of 0 and a slope of 4. So I call that continuous because it looks just like this. Y-intercept of 0 and a slope of 4. I'm going up 1, 2, 3, 4, and over 1 every time. Okay, so this is continuous. If you graph just an explicit function, you're going to graph it as a solid curve rather than a dashed line. Now, what's the domain? Well, since it's continuous, instead of using set notation, we're going to use interval notation. So the domain is all x in, and I'm going to go an open bracket on both sides because I know you can't see it on the window I have right here, but this is implied that we're going to go forever in this direction, meaning my x's are going forever towards the left or approaching negative infinity. Now we can never reach negative infinity, and that's why I must use a parenthesis right there. And guess what? There's another arrow on the right. So on the right, my x values, how far am I going horizontally? To infinity. And there's our domain right there. So look at this. We actually have 3 models again, and it said give at least 2 reasons for your answer. Well, we have 3 reasons. We have the equation of the form f of x equals mx plus b. That's slope-intercept form of a line or a linear function. We have a table that shows a common difference of 4. All right. So again, if I have a common difference, I have a slope, and that means I'm linear. And then when we graphed it, what are we looking at? A straight line. Awesome. Okay, number 4. All they told us is that this function is decreasing at a constant rate. Well, doesn't that mean I have a common difference? All right, so let's think about this a second. The function is, well, if I'm decreasing at a constant rate, that tells me I have a common difference, and I'm decreasing, so that common difference would be a negative number. I'm subtracting or adding a negative every time. And they did not tell me what that rate is, which is the same thing as a slope or a common difference. So I'm just going to call that some parameter a. I don't know what it is, but I do know there's a common difference that is a negative number a. I'm decreasing at a constant rate, so that's linear. Now, I need another reason. So this gets a little abstract, but I'm going to do a graph now, okay? And I'm going to call my inputs x and my outputs f of x. And I'm going to scale my x-axis. I'm going to make every hash mark worth 1/2. Okay. And now because they just gave me a constant rate, but they didn't tell me what that rate was, I'm going to scale my f of x axis using a's. So I'm going to do, watch this, 1a, 2a, 3a's, 4a's, and 5a's. And they also did not tell me what my y-intercept would be, so let's just let b equal 5 times a. So that means my y-intercept is 5a, right there. And do you see what's happening right here? Okay, I just plotted all those points right away because look at this. The common difference is negative a, and the common difference is the same thing as a slope. So that means I am dropping a and I am running 1. Dropping a, running 1. So let's show that with our solid line. And by the way, also, right, decreasing at a constant rate is all they told me. So I am really making an assumption here. I'm conjecturing that this would be continuous. But if you guys put a dash line and said it was discrete, I don't know if I could argue with you because this is pretty vague, decreasing at a constant rate. But I'm going to call it continuous. And if I look at the slope I just talked about there too, m equals, let's put a slope triangle from any two consecutive points. Do you guys agree? One more time. Are we dropping negative a? And are we running 1? Slope is rise over run, so that's negative a over 1, or again, negative a. And look at what we have right here. The common difference and the slope are always the same thing. All right, so there's my 2 reasons right there. Now, let's get back to, I'm conjecturing that this is going to be continuous. And I want it to be continuous because I want to talk about my domain in interval notation. So the domain is x is in the open interval. And now do you notice that I put the arrows on my line to the left? So to the left, x is going towards negative infinity. And to the right, x is going towards positive infinity. And because I can never reach negative infinity or positive infinity, I must make this interval open, meaning I'm going to use parentheses on both ends. All right. If I could equal a number on either side, I would need a bracket on that side. So look at the model they gave us for number 5, a graph. Okay. Now, this curve, right? It's not a straight line, but is that exponential? Doesn't an exponential curve usually look like exponential growth would start somewhere on the y-axis and then slowly turn upward, something like that? And doesn't all of our exponential decay graphs start somewhere on the y-axis and then work down towards the x-axis? But never quite reach it, something like that. So this is neither of those. So I'm going to say this function is neither because, and my 2 reasons, I'm going to keep it real simple. Well, the graph does not show exponential growth or exponential decay. All right, and number 2, the first thing we thought is the graph is not a straight line. The graph is not linear. Okay, but what I want to talk about is then, is this graph the graph of a continuous function, a discrete function, and what's the domain? So it looks to me like we have a solid curve here. That implies we're continuous. All right, and because we're continuous, our domain, we're going to use interval notation. And now we're going to have to make a couple conjectures here. Now, a graph like this usually starts on the x-axis and then works up and then goes on forever like that. And they tried to show that by having the point right there but nothing going through it, and then the line going slightly through that point right here. I can clear that up a little more by going, okay, the graph stops right there. So what is my first x value on this graph? It's a 3. And did you notice that because x can equal 3 in this graph, I used a bracket? But then the graph goes through this point, so they're implying that there's an arrow right there and it just goes on forever. So that's going towards infinity. And because we can never reach infinity, we put a parenthesis on that side. That means it's open on that side. So this is called a half open interval from 3 to infinity. And x can never equal infinity, so it's open on the right. Very cool. Okay, number 6. A person's height as a function of a person's age from age 0 to 100. Now this is very general, so I had to model a situation in my world. So what I did is I'm going to graph the model of my son's height, and I'm going to go age in years and then height in feet. All right, and I just approximated these from memory, but this is my son's data, and it only went to 20 years of age because he was about done growing when he was 20. All right, and there's my height right there, and he's above 6 foot, so I just scaled it to go 1.5, 3 foot, 4.5 feet, 6 feet, and 7.5 feet. So my son's data. Now, here it is. And again, I forget what I approximated these as exactly, but again, these dots will represent my son's height at 0, 4, 8, 12, 16, and 20. Now, look at this graph. Once you have a graph, and by the way, don't you think that the graph of my son's height would be continuous? He's growing continuously. Something like that right there. Okay, now, what does that graph look like? Now think about things like linear curves and exponential curves. The function is, now I don't know about you, but I don't think that is either linear or exponential. So I'm going to say this is neither, because all right, the data I collected does not have a common, well, think about this, all right? Am I adding the same number to my y value every time? No, I am not. If I was, that would be a perfectly straight line. So there's no common difference or a common ratio. Am I multiplying by the same number every time? No, I'm not. If I was, this would be exponential. It'd be doing something more like this right here. So there's no common difference or common ratio right there. All right. But now, more important, the graph is not, and this is kind of how I've answered this common difference or common ratio by using the graph, but I'm picturing graphs of linear and exponential functions. And I'm going to go back to mainly our previous module. Okay, this was the graph that we created for growing dots. Notice it's a perfectly straight line. So that is linear growth. That obviously does not show linear growth. All right, now how about exponential growth? Well, in growing dots, we had this exponential curve right here, and that's an exponential growth curve. This does not look like that, but this is an example of exponential growth. How about linear decay? Well, in the 2.1 launch, we did our first linear decay problem, and that was, remember, my raft going through Oak Springs, hit a sharp rock, and I got a hole, and I was losing air pressure at a constant rate. So I had a common difference. So that was linear decay. And then finally, okay, what was this one right here? This was chew on this. Oh, I remember. This is when, what was his name? Gloop. Was it Augustus Gloop? All right, was dealing with the candy and such, okay, and all right, he was giving away candy or something like that. So, and this was an example of, look at that curve, that's exponential, but it's exponential decay. And this curve doesn't look like any of those models, and this would be the shape of linear growth, linear decay, exponential growth or exponential decay. So the graph is not linear or exponential. But I want to add one thing. It is continuous. And what's the domain? Well, in a way, they gave me the domain from age 0 to 100. Now I'm going to write this appropriately. So the domain is all x in the closed interval. When Jacob was born, he was that tall right there, whatever that decimal may be. And then let's say at age 100, so we're going to assume he's going to make it to 100. Who knows, his generation, maybe people will be living that long more often. I don't know. All right, so at age 100, well, you guys know you don't grow forever. So he's probably going to stay, about 6'4", which is what he is right now. So there it is. All right, that's a great problem right there. All right, and I hope you don't mind I added these graphs over here too, because I just wanted you to have a visualization of linear growth, linear decay, exponential growth, and exponential decay, all on one slide. And I wanted to bring back things we did previously, growing dots, growing dots, one of our launches, and chew on this. Okay, so the model they gave us for number 7 is simply the equation negative 3x equals 4y plus 7. All right, now that's an equation in terms of x and y, but it's not in point slope form or slope intercept form. So let's see if we can put this in slope intercept form to determine what this is. So that means I'm going to solve for this y right here. Okay, so if I was going to solve for this y, remember we're doing the opposite of GEMDAS, all right? We always have to get rid of addition or subtraction first. So do you see this plus 7 right here? We need to get rid of that. So let's subtract 7 from both sides of this equation. And we show that just like this. And then we bring down our equal sign. And on the left, we would have negative 3x plus negative 7, or negative 3x minus 7. And on the right, we have 4y's, and the 7 and the negative 7 cancel each other out, so just 4y's. Now, we're still solving for this y, so we're thinking, what undoes multiplication? Let's divide both sides, and let's divide both sides by 4. Equals, and now I'm going to bring this over here, and I'm going to put my y on the left-hand side of the equation over here, but look at this. 4 times y divided by 4, those 4's will cancel out and give us a y equals. And then on the right, I'm going to put this expression right here, but I'm going to put it in my slope-intercept form. So see the negative 3x being divided by 4? I'm going to write that negative 3/4 times x. So I can clearly see my slope of negative 3 over 4. And then see the negative 7, it is also being divided by 4, so that gives me my y-intercept of negative 7 over 4. And there it is. That's slope-intercept form of a line. So the function is linear because the explicit function is of the form, well, right here it wasn't in this form, but we put it into this form. And what is this? This is your old slope-intercept form of a line. F of x equals mx plus b. Now number 2, well, I'm going to need another model. So why don't we practice graphing lines? It's been a while since we went from an explicit formula to a graph, but again, know the parts right here. The b is my y-intercept. So my y-intercept is going to be negative 7 over 4. All right, and to plot that, I better scale my graph. So I'm going to scale my x-axis and my f of x-axis. So let's scale the x's like this. Okay, and then f of x, I'm going to have some positives and some negatives down here. All right, so negative 7 over 4. Well, all right, you might see this better as a decimal or a mixed number. Would that be negative 1 3/4? So negative 1 3/4 would be right in here. There we go. All right, and now what's my slope? Well, slope is rise over run, so I'm dropping 3 and I'm running 1. So let's just drop 3. 1, 2, 3, and then run 1, all right? And that's going to be, or excuse me, I'm running 4, 2, and 4 right there. And now 2 points determine a line, so I'm going to get my ruler out and I'm going to draw a straight line between those 2 points. And look, I even put an arrow on both ends, telling the world it's going to go on forever in both directions. All right, so my second reason that this is linear is because the graph is a straight line. The graph is linear. Now, this is a continuous function because I started with just an equation, and if I do that, I am assuming that it will be continuous. I just find my 2 points and I draw a straight line through those 2 points. All right, and then my domain, this is my favorite domain right here. I have an arrow going forever to the left and an arrow going forever to the right. So x is in the open interval, and I have to go open because x can never reach negative infinity to the left, nor can it reach infinity to the right. Thank you. Again, number 8, they gave us a table. All right, that's a great model, except notice what they're doing to make things just a little bit more challenging for us. The x's begin with a -2, and then they're not going by ones here. They're going from -2 to 0 to 2 to 4 to 6. So I can't go over here and look directly for a common difference or common ratios because my x's are not increasing by ones over here. So I get to show you something new on this table right here to determine whether or not we are linear. Okay? This symbol right here means, well, we say it delta x, but what that means is the change in x. So what is the change in every x in this table? We're adding 2. The change in x is 2. And guess what we're going to do for our y's? The change in y. And what is the change in every y? Well, 23 goes to 5, 5 goes to -13, and so on. It looks to me like we are subtracting, and what would that be? 5 plus what number is 23? Aren't we subtracting 18? The change in y is -18. Good. Now, I already know this is linear right now, and let me explain how. The function is linear because, well, if the change in x and the change in y are both constant values, my x's are always increasing by 2's, and my y's are always decreasing by 18's, then I know I must be linear. So we're going to say that. The change in x and the change in y are both constants. The change in x is 2, the change in y is -18, so it has to be linear. Now, let's find one more way to show this. Okay, how about we go to our equation? Now, if the function is linear, then we know we can write it as y equals mx plus b. So my first thought is y equals mx plus b. M, what's the slope? Well, believe it or not, with these two expressions, I can see the slope already. And let me explain that. Okay, slope is, we'll go back to the 7th grade. Slope is rise over run. And guess what the rise is in this problem? It's the change in y. You get it? Y measures vertically, so rise is the change in y. And what's the run? That's the change in x. So the change in x. Rise over run is the change in your y values over the change in your x values. And now, let's just think about that. That would be the fraction -18 over 2, which we could reduce to -9. So the slope that this table models would be -9. That would have also been the common difference had we had our x's just increased by 1. And now, the b is the y-intercept. And when x equals 0, what does y equal? Look at that 5 right there. Plus 5. Now, there's my 2 reasons why this must be linear. It is linear because the table shows that the change in x and the change in y are both constant. And the equation for that table would be y equals negative 9x plus 5. Now, let's talk about continuous versus discrete. Remember, I have to use their original model to make this decision. And since they only gave me a table, I am going to assume that would be discrete. My inputs are whole numbers and my outputs are whole numbers, or I should say integers here. So discrete, and now let's talk domain. And the domain of a discrete graph, that's my favorite, is just the set of all my x values in the table. So the domain is all x in the set, negative 2, 0, 2, 4, and 6. Oh, that's a great problem. Okay, number 9. Number 9 is one of my favorite problems because they started us off with a model that this table is not set up to be user-friendly. It's just a collection of data. It looks to me like somebody just started measuring people. Like this first person had a height of 62 inches and a shoe size of 6. The second person was 74 inches tall with a shoe size of 13, and so on. Now, because the data is not organized, all right, I really can't determine just by looking at the table if I have a common difference or a common ratio. So I need to take this data in a very unorganized table, and how about if we graph it? Because a graph will tell me everything I need to know. All right. Oh, notice this too. Broken x-axis and a broken y-axis. That's the first time we've broken both axes. All right. And you need to know what's going to go on the horizontal axis. Well, my first column is always the horizontal axis. So this measures height in inches. And then the vertical axis is always your second column, or the shoe size. And now I skip some numbers. What? My lowest height is 53, so I probably started with a 50 out here somewhere. So let's see. Yep, 50, 60, 70, and 80. And now my shoe size. Well, my smallest shoe size is a 4, so I probably put a 4 in here somewhere. Let's find out. Yep. And now I can carefully plot my data. So at 62 inches tall, we have a shoe size of 6. So let's go 62 and then up to 6. About right there. Okay? And then at 74 inches tall, we have a shoe size of 13. Well, that's going to be way up here. Oh, it's even off my grid, so I'm going to approximate that about right here. Okay. At 70 inches tall, we have a shoe size of 9. Right there. At 67 inches tall, we have a shoe size of 11. Random data. 67 and then up to 11. Let's be careful here. 67 and 11, about right there. Okay. And 53, we have a shoe size of 4. Well, there's 55, 53, 4, about right there. And at 58, we have a shoe size of 7. So 58 and then 7, about right here. Okay, well, does that scatter plot look like a scatter plot for a linear or an exponential function? The function is, well, linear functions form straight lines. That definitely does not form a straight line. And exponential functions will either show exponential growth or exponential decay. Those are both smooth curves with some concavity, and this does not show that either. So this function is neither, because the graph is not linear or exponential. Okay, reason number 1 with our simple graph. Now, reason number 2. Let's see. Well, the table. What else could I do? Well, do you agree if I went out and collected even more data so I could create a more user-friendly table. Let's say I found somebody that was 53, 54, 55, 56, 57, and 58 inches tall, and I put that right here for my height, and then their shoe sizes right here. All right. Well, based upon what I have in this sample, there is no way that would show me a common difference or a common ratio. So the data does not show a common difference, which would make my function linear, or ratio, which would make my function exponential. All right. Now, let's go to the stuff that I'm adding here, discrete versus continuous. Now, typically, when I start with a table, I'm assuming I have discrete data. I have inputs and outputs that are just whole numbers, just like I see here. But this table has a story because this is height in inches and shoe size. And do you agree? As you grow taller, you're doing that continuously. And as you are growing taller, do you agree that your shoe size is growing continuously? So even though we started with a table, I'm going to call this continuous. And that means my domain will be interval notation. All right. And now, because of my lack of data, I really can't tell what my minimum height is and my maximum height is in inches. So I'm going to go back to the problem we did earlier with the graph of my son's height. Here it is right here. And this is in feet, but we'll convert to inches or do our best. Now, that would be like 1.5, so that's a little over 1.8 right there. So 1.8, a little more than that. And my son was born, I believe, I know it was a long time ago, almost 23 years ago now, but if I remember right, I think he was 22 inches tall when he was born. Okay? And then he was always tall growing up, and then he became a pretty big time basketball player, and he stopped growing at about 6'4", which was 76 inches tall. And that's what he is today. All right, so that's a great problem right there. And I hope you guys don't mind all the extra that I'm adding. I'm just using everything we're doing to review everything we have done and take you in directions we are about to go. So, number 10. Sorry, my dog is barking in the background, which means the big dog that's in my office in a kennel right now might start barking too. So if that happens, please accept my apology. Anyway, number 10. The number of cell phone users in Centerville as a function of years if the number of users is increasing by 75% each year. All right, as soon as I see users are increasing by 75% each year, I already know that I am exponential. We're growing exponentially. The function then is exponential because, well, if I am increasing by 75% every year, then I have a common ratio. And that ratio, now be careful here, a lot of people will say that would be 0.75, but that would be actually exponential decay. If I'm increasing by 75%, then my common ratio is 1.75. The 1 represents 100% of the users, and the 0.75 represents my increase, 1.75. Okay? Now, part 2. How am I going to do this? Now, let's think about this. Okay, let's go a recursive model here. Let's see if we can see a pattern of change in a recursive model. Okay, I like this. So I'm going to say f of, and let's just say whatever year we started collecting this data, we're going to call that year 0. And I do not know the number of cell phone users in Centerville in year 0, so I'm just going to say that f of 0 equals some number a, whatever that may have been. And then my recursion equation would be f of n equals f of n minus 1 times, because I have a common ratio, and what are we multiplying by every time? 1.75. So The recursive formula shows me the pattern of change right here in the recursion equation. The previous number of cell phone users will always be multiplied by 1.75. That tells me I'm exponential. So the recursive formula shows the pattern of change is multiplication by the same number. In this case, it will always be 1.75. Now, let's talk discrete or continuous. All right, so I'm going to say discrete now because, again, the number of cell phone users, okay, will always be a whole number. All right, 150 people, 300,000 people. Those are always whole numbers. All right, now the years are changing, and years change continuously. But our data would be like year 0, year 1, and so on. So we're going to call this discrete. Now, discrete, that means my domain will be in set notation. So I'm going to say X is in, and I'm going to start at year 0. That might have been like 2010, who knows. Year 0, year 1, year 2, year 3, year 4, and so on. And that would go on and on and on until I'm done collecting data. Or maybe in this case to the year 2020. Okay, so great problem. Okay, so number 11, the model is this beautiful graph right here, and this is a nice graph. All right, so what does this model? Does this graph represent a linear function, an exponential function, or neither? Okay, well, look at this shape. Notice the concavity. Notice the smooth curve. All right, and think about all of the models we have been working with. Here's some examples right here on the right. Doesn't this graph look very similar to this exponential growth graph right here from growing dots? Guess what? The function is exponential. Why? The graph shows not only exponential, but exponential what? Growth. Okay, now for a second reason, I'd better go to another model. So why don't we take this graph and create a simple table? Okay, and let's just start with, and notice how, remember the table we had earlier that had X's all over the place because that was height in inches and people collected data randomly? Nice and organized, 0, 1, 2, and 3. So at X equals 0, what is my Y? That point right there, which would be a 1. When X equals 1, what is my Y? It looks like a 2. When X equals 2, what's my Y? Oh, this is pretty. That's going to be a 4. And when X equals 3, what is my Y? I'm betting that's an 8. Sure enough, 8. There we have it right there. So look at the data, look at your Y's, or you could have called those f of x's if you wanted. What's my pattern of change? Are we multiplying by 2 every time? If so, r equals 2. There's my 2 reasons. That graph must be the graph of an exponential function, and we've just proven it with that table. Now, discrete or continuous? Well, notice this is a solid line, so it's continuous. And if I do the domain of a function whose graph is a solid line or a function that is continuous, I'm going to use interval notation. So the domain is x is in, all right? And now, remember, they don't usually put these on the graph, but I'm going to put an arrow there. So my x's are approaching negative infinity to the left. And an arrow up here, which means, yeah, it looks like I'm going up, 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 but I'm also working to the right forever and ever and ever to infinity. And that's exclusive, and that's why we use parentheses. We can never reach negative infinity over infinity. Okay, number 12. The time it takes you to get to work as a function. Ooh, there's a typo in your curriculum right here. I think that should be as a function of the. So let's put a little of right there. See, even doctors at Stanford University make typos. That's okay. Of the speed at which you drive. Not a lot of information right here. the time it takes you to get to work as a function of the speed at which you drive. Wow. All right, well, let's try to model this. This is very general, so let's do a very general model. And to model this with a function, hopefully you've studied a little bit of physics. Do you guys agree that distance equals rate times time? I think you've seen that formula before. All right, now they want time, t, in terms of the speed at which you drive, so that's t in terms of r. So I'm going to take this and solve for t. So that implies t equals, well, let's divide both sides by r. That means t would equal d divided by r. So the time it takes me to drive anywhere is the distance I travel divided by the rate at which I am driving, or my speed. All right, and that's assuming that I'm driving at a constant rate, which is rarely true around here, but let's make this simple. All right, now let's take a look at this. Does that look like y equals mx plus b, or y equals a times b to the x power? That is not linear or exponential. In fact, this is called inverse variation, because d is a distance, that's a number. All right, r is a variable and t is a variable. And whenever I have a variable equal to a number over another variable, that's called inverse variation. You're going to study that in IM3 and pre-calculus, okay? So, not linear or exponential. That implies it's a neither, all right? And let's try to use one more model to show this. So I'm going to have to create more of a story problem here so I can really create a table. So let my distance to work equal 20 freeway miles. Now, when I went to the University of Portland, I worked part-time at a restaurant in Woodland, Washington called the Oak Tree Restaurant. Still there today, by the way. All right. And I lived in Vancouver, and it was 20 freeway miles for me to get to the Oak Tree Restaurant. So I used that to set up things here. So let my distance to work equal 20 freeway miles, and my average speed is the rate in miles per hour in which I drive on the freeway. Okay, let's crunch some numbers. So let's put my input as my rate, because that is my independent variable, r. So that's my rate, and that's in miles per hour. All right, and then my output is my time. How long is it going to take me? And that equals my distance divided by my rate, and time is going to be in hours. Okay, so now all we have to do then for each of these outputs is take the distance, which is always going to be 20 miles, and divide it by the rate. And then let's reduce the fractions. So let's use our calculator. And you guys, make sure you can reduce fractions on your calculator. I'll probably work with a few of you on this when we're asynchronous, okay? But I'm going to take my distance 20, and I'm going to divide by 60. And that one I can do in my head, but some of these will be a little more challenging. So 20 over 60 would be 10 over 30, be 5 over 15. Would that be what, 1/3? So it's going to take 1/3 of an hour for me to get to the Totem Pole restaurant. Excuse me, the Oak Tree Restaurant. I also worked at the Totem Pole for some time. Okay, now the Totem Pole, by the way, is not there anymore. That was a long, long time ago. Let's do the same thing. Let's go 20 divided by 55. So 20 divided by 55, and I get a decimal, and I'm going to have my calculator give me a reduced fraction. And my calculator is saying that's 4 over 11. Okay, we could have figured that out without a calculator too, by the way. All right, and now let's go 20 divided by 50. 20 divided by 50, and I'm going to get the fraction 2 over 5. And then 20 divided by 45, and I'm going to get the fraction 4 over 9. Wow. And then one more, 20 divided by 40. Well, I think we can handle that. That's a 1/2. All right, there we have it. That's a great table right there. Now, first, I want to check, could that possibly be linear? All right, and notice that my R's are not like in order or increasing by 1, so I can't just go over here and look for a common difference. So I've got to do the change in R and the change in T business. So the change in R is, well, my R's are decreasing by 5. That's constant. Delta R is -5. But what's delta T doing? I'm not decreasing or increasing by the same number here. I went from 1/3 of an hour to a half hour, all right? But not by the same interval every time. But delta T is not constant. So that tells me it cannot be linear. Now, one more thing. What about a possible common ratio? Well, even though my R's are not in order and increasing by 1s, I can look to see if I have a common ratio because it is constant over here on the left. So I'm going to go 4/9 divided by 1/2 and see what I get. 4 divided by 9 divided by 1 divided by 2. That's a complex fraction. And I'm getting 0.8 repeating. Or, by the way, math fraction, I'm getting 8/9. Now, if there is a common ratio, then if I go 2/5 divided by 4/9, I should get 8/9 again. So let's find out. 2 divided by 5 divided by 4/9. 4 divided by 9. And, oh, I'm close, but not quite. I get a 0.9 or a 9/10. So there's no common ratio either. So that has proven that this situation will never be linear or exponential. Okay? The function is neither. So let's talk about continuous versus discrete. Okay? Well, that was a little premature right there. But if you look at my rates, all right, which is my input, okay, when I get on the freeway, I'm accelerating until I get to 60 miles per hour. That's continuous. And these times, well, the faster I go, the quicker I'm going to get there. So these times are also changing continuously. So I'm going to say that this is continuous. And now, how about the domain? Well, the domain of a continuous function, we would use interval notation. And I'm going to show you my good driving record right now. I'm at the stoplight, waiting to get onto the freeway. So I'm beginning at 0 miles per hour, a rate of 0. And then when I get on the freeway, I accelerate until I get to 60 miles per hour. So that's my domain between 0 and 60. Okay, and that's inclusive, and that's why I did brackets. X can equal 0, or in this case R, and R can equal 60. Because Mr. Gibbons does not break the law on the freeway. You know, I'm a certified driver's ed instructor as well. All right, that's kind of a cool problem. Okay, it's getting late and my family's getting a little irritated. I've been recording all afternoon and they would like some help with dinner and such. So I'm going to try to expedite things just a little bit, but I promise I won't leave anything behind here. So number 13, all they did was give us the equation y equals 7x squared. Now does that look like y equals mx plus b? No, it does not. So we cannot be linear. Does that look like y equals a times b to the x power? Why, no, it does not. So it cannot be exponential. So the function is neither because the explicit function is, and you haven't studied a function like this yet, but you will next year, and this is called a quadratic function. It's quadratic. All right. Now, let me do another model so I can prove to you that there won't be a common difference or a common ratio. So my table is going to have my x's in order with a change in x of 1. So I just did something like this. X is -2, -1, 0, 1, and 2. And now let's do direct substitution. Negative 2 squared would be positive 4 times 7, 28. Negative 1 squared, well, negative 1 times negative 1 is 1 times 7 is 7. 0 squared is 0 times 7 is 0. And now watch what happens. If I square 1, I get 1 times 7 is a 7. And if I square 2, I get a 4 times 7 is a 28. Quadratics have what we call symmetry. That's why you see it's decreasing 28, 7, 0. And then it's increasing from 0 to 7 to 28. A quadratic function will always do something like this. Okay, so the common difference. Well, again, my x's are in order, and the change in x is 1, so I can look for a common difference. All right, and I am decreasing, but not by the same number, and then I'm increasing, but not by the same number. There is no common difference. Common ratio. Do I see a pattern of change where I'm multiplying by the same number every time? Not if I'm decreasing and then increasing. There's no common ratio either. So this is neither. And here's my two reasons. And now let's go discrete versus continuous. Remember, we started with just a function, so we're going to assume we're continuous. And the domain of a continuous function, we use interval notation. The domain is x is in, and we're assuming we're going to go forever in both directions. So I'm going to go from negative infinity to infinity exclusive. All right, this is number 13. Number 14. Each point on the graph is exactly 1/3 of the previous point. Well, points on a graph, those would be measuring my outputs. And if every point is 1/3 of the previous point, don't I have a common ratio? So I'm going to say the function is exponential because the common ratio would be, well, I'm going to multiply by 1/3 every time. 1/3. Now, if I graph this situation, I'm going to show a graph that will have exponential decay. So let's see. Let's go my inputs and my outputs, f of n, and let's scale both axes. So I'm going to go 2, 4, 6, 8. So I'm going by ones there. And I'm going to let f of 0 equal 6. So let's make sure this gets up to a 6. There we go. That'll work. Now, if I let f of 0 equal 6, then here's my first point on this graph right here. Okay, and by the way, one click and I'm putting all the points here. So look what I did. Each point is 1/3 of the previous point. Okay, so 6, well, what's 1/3 of 6? It's 2. What's 1/3 of 2? It would be 2/3. What's 1/3 of 2/3? That would be 2/9. And what's 1/3 of 2/9? That would be 2 over 3 times 9, 27, 2/27. So there is my graph right there. And does that look like exponential decay to you guys? The graph has an exponential shape. There we have it. Now, let's talk about discrete versus continuous based upon everything they gave me. And they're just talking about points, all right? But, and you know, 1/3 of the previous, and I do agree, my outputs are fractions, but they're not talking about anything in between any of these points right here. So I bet you I said discrete. I did. And discrete means I'm going to use set notation for my domain. So the domain will be x is in, and just look at my graph. My first x, or my n, in this case on the graph, would be 0, and then a 1, and then a 2, and then a 3, and then a 4, and so on, because this graph could keep going and going and going, and my dots would just get closer and closer and closer to this n axis right there. Awesome. All right, number 15. Wow, they're giving me, this is interesting. This is another form of a recursive formula. And you haven't seen this before, so I'm glad we're talking about this right now. Okay, well, I have two initial terms here. F of 1 is 7, and then f of 2 is also 7. And then my recursion equation is f of n is the previous term plus the term before that. So let's see if we can take this and create a sequence, and then we'll be able to answer the question. So f of 1 is 7. My first term is 7. F of 2 is 7. My second term is 7. Now, what's my third term? And this is why I needed two initial conditions. My third term is the last term plus the term before that. So this third term would be 7 plus the term before that, 7, 14. And now this term then would be 14 plus 7, 21. And this term would be 21 plus 14, 35. And that pattern would continue. Oh, that's cool. But by the way, that's not linear or exponential. Why? Because I don't see a common difference or a common ratio. The common difference does not exist, and the common ratio does not exist. All right? So how could we show that in another way? Well, excuse me, we've got this great sequence right here, and these are outputs in a graph. So let's just do a quick graph. Okay, and my input will be, how about we call it n? My outputs will be f of n. Okay, and I need to scale my n-axis. So I did 2, 4, 6, 8, 10. I like that. And my y-axis, well, I've got to get up there pretty far. So let's see. Yeah, that should work right there. Okay, now let's start plotting our points. So remember, this is my first term. So when n equals 1, I'm going to be at 7. That's 8. That's 4. So 7 is going to be right in there. And at 2, I'm still at 7. And then at 3, I jump to 14. So that's 12. So 14 is going to be right in here. And then at 3, I'm going to jump up, or excuse me, at 4, the fourth term, I'm going to jump up to 21. So there's 20, 21, about right there. And then the fifth term, I'm going to jump all the way up to my 35. So that's 36, so 35 is going to be about right there. Now, I agree that almost looks exponential, but do you see how I'm constant right there? That's flat. And then I start doing a smooth curve. So that graph does not show a pattern that is linear or exponential. The graph is neither linear nor exponential. Now, let's talk domain, range, and continuous discrete. Okay, well, I have to use what they gave me, and that is just a recursive formula, which is nothing more than shorthand for a table. Inputs and outputs look like whole numbers, so I'm going to say it's discrete, which means my domain will be set notation. So the domain is n in, and, well, first term, second term, third term, fourth term, and so on. And there it is right there. Okay, number 16. Oh, another recursive formula. Right on. All right. Let's see, did I start with a sequence again? Okay, well, I'm going right to the answer, so let me go back here. Okay, so f of 0 equals 1, and f of n plus 1 equals 2/3 times f of n. Ooh, they're changing it up a little bit. They're calling the term we're looking for f of n plus 1, and the previous term f of n. That's interesting. But do you see this 2/3 right here? I'm multiplying the previous term by 2/3. That's a common ratio, so this is going to be exponential. So the function is exponential because the common ratio is 2/3. Okay, now another model to show that. It looks like we're going to go ahead and graph again. So let's go n, f of n, and let's scale the n-axis. Looks good. Now, I'm starting with a 1, so let's scale this like, okay, I've got to end up at 1 somewhere on the top. So what did I do? Oh, there we go. All right, great. So f of 0 is 1. Now, f of 1 would be 2/3 of the previous output. So what's 2/3 of 1? that would be 2/3, which is 0.75. So there's 0.8, so there's 0.7, so 0.75 would be right there. Nice. Uh-oh, I missed that. Oh, 2/3. I just did 3/4. I'm sorry, I'm getting so tired, you guys. 2/3 would be 0.6 repeating, so that's right here. Okay, now, 2. Well, 2/3 of this number, so I need 2/3 of 2/3, which would be 4/9, and I'm going to go ahead and do that as a decimal right now so I don't make a mistake. So 2 divided by 3 times 2 divided by 3, and I'm getting 0.4 repeating. So let's see how I did. 0.4, all right, that's 0.5, so 0.4 repeating would be right in here somewhere. Look at that, right on. I'm hot now. And now at 3, I'm going to go 2/3 of that number. So I'm going to go 2 divided by 3 times my last answer. And I'm getting 0.296, 296, 296, or 0.296 repeating. So almost 0.3. So it's going to be almost right here. Whew. All right, awesome. And then I don't know how many more I'm going to do. I probably did a few more here. Let's find out because I want to see the concavity. So let's go 2/3 of that decimal. So I'm going to go times 2 divided by 3. And I'm getting 0.19753086642. Woohoo! Almost 0.2. So almost up to this right there. Did I do another one? Let's see if I did. Okay, so times 2/3. And I'm getting 0.131687248. So 0.13. Let's see if I did that. Well, that'd be 0.1. 0.13 would be about right in here. I didn't go any farther. All right, but anyway, the graph has, now do you see what I see? Nice and smooth, but not straight. That's exponential decay. So this is an exponential shape, just like we expected. All right, now let's talk discrete versus continuous. Remember, they started with a recursive formula. That's just inputs and outputs. Okay, nothing in between. So we're going to say discrete. And the domain is x is in. And my first x was a 0 this time. And then 1, 2, 3, 4, and so on. And that is 2.3. Wow, I hope you enjoyed it. You guys have a great day.